so we move on to our last presentation for today, for this session. This is by Kyungwan Shim. He works on nota.ai as a deep learning engineer for the Netpresso compression toolkit. And he will be presenting his work on toward compact deep neural networks via energy-aware pruning.
Hello everyone, I'm Kyungwan Shim from nota.ai. Today I'm going to present our paper toward compact deep neural networks via energy-aware pruning. Our work will be presented as follows: introduction, proposed methods, experimental results, and short demo. As you all may know, the deep learning model shows a great success on the various tasks, but higher computational costs hinders the real-time application of edge devices. Therefore, there are many attempts to avoid these issues by using quantization, logic distillation, static compression, and pruning. Quantization reduces the number of bits required to represent the weights. Logic distillation, training and compact neural networks with distilled knowledge of a large model. Static compression converts the network parameters into lightweight representations via low-rank approximation. And pruning remove redundant or non-informative parameters to accelerate and compress the model. Pruning, to be more specifically, can be divided into two types: structured pruning and the structured pruning. Structured pruning removes each individual weight into zero, so it can prune more weights without performance deterioration. However, it needs additional devices or hardware or library to accelerate the model. On the other hand, structured pruning removes entire filters or channels. Therefore, it doesn't need additional hardware library to accelerate the model. However, structured pruning removes a lot of filters or channels. It may reduce the performance of the model. Therefore, we propose a novel energy-aware pruning criteria for filter pruning. And we could achieve the state-of-the-art performances with similar compression ratio over a variety of conventional pruning approaches. Furthermore, we verified that our proposed method is consistent regardless of the data quantity and the quality. Let's take more look about our proposed methods. Actually, conventional pruning approach has 3 steps. Prepare the original model, and compress the model by using certain criteria, and fine-tuning the model. Similarly, our proposed method also follows the conventional pipelines, but with push-up data sets. First, need to prepare the original model with the push-up data set and calculate each filter's feature map, calculate the nuclear node of each filter's feature map, and remove less informative filters. And last, fine-tuning the compressed model to compensate the performance loss. We assume that the model requires certain amounts of energy to extract meaningful information from the image. Therefore, we employ energy as our pruning criteria, which is also known as nuclear norm. The nuclear norm is the summation of the singular values, which usually used to represent the matrix and solve the matrix complex problem. The right figure is the features that survived by L2 norm and the nuclear norm, and we could find out that the least amount of the we could remove less informative information filters. We could prune it. Let's take the results of the proposed methods. To compare the proposed method with the conventional approaches, we run experiments on the CFR10 and immediate data set. We see the experiments on the CFR10, as you can see here. We compare against several popular CNNs such as VG16, Resident 56, Resident 110, GoogleNet, and DESNet 40. Our proposed methods could outperform the conventional approaches with smaller and faster model. Additionally, we also conduct the experiments on the Resident 50 with immediate data set for more complicated cases. We could see that our proposed methods could achieve could surpass conventional approaches more than could surpass the conventional approaches. As our proposed method is calculating the nuclear norm on the filter's feature map, the data used can affect the performance of the compressed model. So therefore, we perform 2 additional ablation studies to verify whether our proposed method is stable or no on the data quality and the data quality. As you can see here, we use the easy data and hard data to verify whether our proposed method is consistent regardless of the data quality. We select a single batch with the lowest loss as an easy data set and hard data set as vice versa. As you can see here, there is no significant difference between compressed model by easy data set and a hard data set. So, which means our proposed method is quite consistent regardless of the data quality. Here's the proposed, the second evolution study is about the data quantity. This is the results of the candle tau distance between filter ranking list of two neighbor batch sizes. Here, so y-axis is the how the rank is changed by the quantity of the batches. So as you can see, it's quite consistent regardless of the data quantity. I prepared for the short demo to adapt nuclear node on your own model. As pruning criterion requires additional cares for pruning element-wise operation, we opened the Nespresso compression toolkit, which helps users to prune your own model by using nuclear norm. Oops. Can we turn on the video? Thank you. In this video, I'm going to describe how to compress and isolate your model by using the nuclear norm. As described in the toward compactive neural networks via energy-aware pruning. First, we need to prepare the model to compress. Here, we can use SAF100 pre-trained resin 50 to compress the model. After preparing the pre-trained model, log into the compression.nespresso.ai. The Nespresso compression toolkit helps the user to compress the model without any prior knowledge on a model compression. Click Models to unlock the model. Here is a list of the models. To upload your model, click Upload Model. As the name of our model is Resin 50, insert Resin 50. The Nespresso compression toolkit supports both TensorFlow and PyTorch as an input. Click Unload the model to unload the model. To compress the model, click Compress button next to your model. The Nespresso compression toolkit provides two compression functions, filter pruning and filter decomposition. However, as we want to compress the model by using the nuclear norm, click Nuclear norm pruning. As nuclear norm is feature mapped to measure the input to score, the nuclear norm pruning requires a portion of the dataset. The dataset can be uploaded in an MPY format, but the file size should be limited to 15 megabytes. Here, we visualize the graph of the model and the prunable layers. User can prune the layer by selecting the layer and inserting the pruning ratio like this. To help user to compress the model more efficiently, we also provide the detailed information of the layer. Furthermore, every commercial layer that is connected by the element-wise operations must be pruned identically. For this reason, we combine those layers into a single element-wise layer, as here. We also provide the recommendation functions to automatically compress the user's model. Let's print 50% of the model. Once the user clicks the recommendation button, MBTA calculates the nuclear norm of each filter and returns the pruning ratio of each layer. last, click the compress button to return the compressed model. The user can check detailed information of the original model and how it compressed. To check whether it pruned successfully or no, let's compare the original model and the compressed model. As you can check at the first layer, the original model contains 64 alpha filters, while the compressed model contains 27 filters. In the case of original connection, all connected layers have the same number of filters, as you can see here. Thank you very much for your watching. Try the Nespresso compression toolkit to compress your model. Thank you. Yep. So it was our demo. Sorry for the occlusion. I actually updated this PowerPoint, but it couldn't update this. Sorry. You can use our method in the Nespresso compression, the Nespresso AI. So feel free to use it. Thank you very much. Thank you for listening.
Did you try using other types of decomposition different to singular value decomposition or other criterions different to the nuclear normal form?
It's all based on the nuclear norm, which is a summation of the single values. So we calculate the single basis at each filter's feature map and measure the imperative score of the corresponding filters.
Okay.
And we are very thankful for our sponsors. The premier sponsor this year is Edge and Pulse. And then executive sponsors are ARM, DeepLight, Qualcomm, and Sentient. Platinum sponsor Analog Devices, BrainChip, Infineon, Clickertech, Latent AI, NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving tinyML forward. And gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SenseML, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors: Yeom Devices, Aspinity, Seva, EMSA, Greenwave Technologies, Gravity, Hymix, HOTG, Imagimob, Itemis, Lattice, Nota, OmniML, PixArt, Plumerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texel, and Google. So we are very thankful for their support and, more importantly, for them being part of this community and driving it forward.